Hi everyone, can you hear me and see my screen clearly? Hi Gaurav, hi Saran. Hi Shilpa, hey Michelle, hey TJ. All right, so should we start? All right, let's start. I'm hoping that others will be joining soon. So today's topic is quite important and all right, Michelle, no worries. The session is being recorded, so you will see the video as well as you will see you can see the entire topic in the self-paced also. Okay. Okay. All right. So although I generally expect that you guys go through the self-paced course as well and finish the exercise there and attend to the videos because that serves as a quick refresher as well as it helps you recall what we discussed here. Okay. All right. So today we are going to discuss something called YARN, yet another resource manager. All right. So far, we have discussed what is storage, and before that, we have discussed what is Zookeeper. All right. So the first and foremost important thing that we understood was how do we coordinate when you have multiple computers. This course is about distributed computing. This course is about big data, which basically means computing on humongous data using multiple computers. All right. So in Zookeeper, we learned how to coordinate between various processes, and Zookeeper is internally used by other tools. And then we discussed HDFS and learned how the data gets distributed on multiple machines to provide a humongous storage, or how a humongous storage is built using multiple computers. So for now you can think of HDFS like a network file system, right? And Zookeeper like a very tiny thin database. And uh, could you mute yourself? Okay, good, good. Uh, all right. And the Zookeeper, you can think of it like a central small storage system, which is very fault tolerant. And then so we've discussed how to store data, but if your data is kept in HDFS, how do we process it? How do we process it efficiently? We can process this data which is in HDFS using the normal way that we retrieve all of this data to our local computer and then process it, right? But that'll be too inefficient, right? Because here we're talking about terabytes of data. Transferring that data to your desktop is next to impossible, right? So how do we do the computation on top of that data, right? That's what is Yarn about. Let's start. Do you have any questions for me before we start the session? Any questions for me? Alan, Asim, Gaurav, Isha, Michelle, Saran, Shilpa, Sauris, SP, and TJ. Welcome to the session. And all right, so feel free to ask questions. Sauris, you had a question? All right. Okay. So there was a question related to like Sandeep Giri folder is not available. Somebody has asked. All right. I forgot somebody has asked that question over our forum. And let me see. All right. If you have any questions, we can discuss that before starting the session. All right. So we learned how to store humongous data in HDFS, but how to process that data is what we're going to discuss with Jan. Okay. All right. Great. So this is the component that we are going to talk about today, which just comes above the Hadoop distributed file system. It's called yet another resource negotiator, right? Yet another, we know what does it mean? Resource negotiator, we will learn, okay? It basically helps us get the resources in a cluster. Cluster is just a bunch of computers connected together in a network. All right, so in the usual format, how much time would it take for 1 gigahertz processor with 1 gigabyte RAM computer to resize 1,000,000 profile pics? Yes? Okay, so there is a computer which has 1 gigahertz processor and 1 GB RAM. It takes around 20 milliseconds to read a pic from the disk and 5 milliseconds to resize. Okay, so 20 milliseconds to read the pic from the disk and 5 milliseconds to resize. And you have got this computer, although the specs are irrelevant. Okay, now my question to you is, there are 1 million such pictures which need to be resized. We have 1 million pictures which need to be resized, and it takes 20 milliseconds to read the picture from the disk and 5 milliseconds to resize. Question to all of you is, how much time would it take to resize 1 million profile pics? Yes? It's very important. It's a very important exercise because the way we look at the computing processes is not same as the way we look at the normal world. There are minor differences. So we need to learn that part. Okay. And by the way, one of my works that I did at Amazon was around a similar phenomenon. Okay. So is the question clear to you, Alan, Asim, Gaurav, Isha, Michelle, Saran, Shilpa, Sauris, SP, TJ? So you have a computer which takes 20 milliseconds to read a file, read a picture from the disk, and 5 milliseconds to resize it. How much time it would take to resize 1 million profile pics? Good question, Silpa. It won't be. 1 million profile pics so cannot be, if the pictures are 1 kilobyte only then we can accommodate them. But my question to you is, do we really accommodate 1 million profile pics in the memory? Right, right. So Saran's point is, read is in one thread. What was that? If one thread, yeah, go ahead. I think you are on the right direction. All right. So Saran's answer is 25 times million if there is only one thread. Okay, but it's not one thread. There are multiple threads in this. We can have multiple threads, right? Even if there is a single core, still we can have multiple threads. Why? A simple answer is that while one picture is getting loaded from the disk, in that time we can process another picture which was loaded earlier, okay, so that the two things can be done parallelly. Reading a new pic and resizing the already loaded one. The two things can be done in parallel, right? If we have multi-threaded system. Because while you read something from the disk is involved. But while you do the processing, only then the CPU is involved, right? While reading the data from the disk, it's not too much of a CPU intensive task. All right. So one of the answers from Saran is 25 million seconds. 25 million milliseconds actually. So it's 25,000 seconds. That's what you want to say. Any other answers? That's the obvious answer. And of course, the question is little twisted. So is the question clear to everyone? So you have got around a million photos, million pictures. You want to resize these using a computer, right? So it involves two phases. One is reading the file from the disk, and other is resizing that file. Resizing is taking 5 milliseconds. Resizing is taking 5 milliseconds while reading is taking 20 milliseconds. My question to you is, how much time would it take? Will it take on an average 25 milliseconds to process a pic, to resize the pic, or it will take 20 milliseconds, or it will take more than that? Yes, feel free to answer. It's a open question. So Gaurav says 20. Sorry, Isha, and okay, they say 20. Anybody else? Right. TJ says that not all resources will be available all the times. So we have to consider the wait time. Okay, let's put some approximation on the wait time, TJ, and then we can consider other parts. So which resources are we talking about while reading the file from the disk? You're talking about disk as the resource. There will be a seek time and there will be a reading time and so on. Is there? Okay. So all of that is kind of, we have considered that while saying 20 milliseconds to read the pic. Okay. So that wait time as well as actual time is in 20 milliseconds and 5 milliseconds. Very good question, Michelle. Yes. So we kind of forgot the writing time. So for now, we can ignore the writing time. Okay. We can think of like we just wanted to resize and then forget the picture. The right. To oversimplify, I actually removed the writing time. Yes. So, okay. Sorry, Isa and Gaurav. Okay, could you elaborate your answer? Your answers are correct. All right. All right, let me do that for you. No worries. Okay. So as I said that the process is stepwise, right? So let's say there are two things, CPU and disk, right? While reading the pic, it's the disk which is involved, but while resizing the pic, it's the CPU and RAM that gets involved, right? So from 0 to first 20 seconds, the time will, so on x-axis it's the time. So from 0 to 20 seconds, the file is getting read from the disk. And then the resizing is starting. Now, while the picture one is getting resized, we can start reading picture two, right? And so on. So from 20 to 40 seconds, we are reading the picture, right? Second profile pic. And then the second profile pic is getting processed. And then we are reading third profile pic. Okay. So how much memory are we consuming? Quickly, at max, how much memory are we consuming? Yeah. Okay. Let me explain once more. So what's happening is, so there are millions of pictures in a disk, right? And we want to do is resize. Now for resizing, you have to first load that file from the disk into the memory, right? So and as we said, it takes around 20 milliseconds to finish loading. So 0 to 20 milliseconds will go in reading the file from the disk into the memory, correct? And then at the 20th second, this pic will get resized in separate thread, right? So there are two threads going on. One is resizing thread, other is reading thread. And these two things can happen in parallel. Why? Because this one is a disk intensive process, while this one is a CPU intensive, right? Therefore, the two things can be done in parallel, right? So at 20th second, we'll start reading the next picture from the disk while first picture is getting processed, okay? It's like two people at work. First one is resizing, another one is loading the picture, right? And then as the time progresses, so you can see that the time that it takes to process the file is insignificant. Why? Because it's done in parallel. So the main time is getting consumed in loading the files, right? Sorry. Make sense to you? So at the end of say 80th second, we would have finished process reading four files and resizing three files. Correct? The fourth file will start resizing at the end of this. Correct? At the end of 80th millisecond, 4 files will be read and 3 files will be resized. Fourth one will start now. Yes, so if there are n picks, then the time is n into 20 plus 5. Perfect. Perfect. So these many milliseconds. Okay. So if n is 1 million, it'll be 20 million plus 5 milliseconds, right? Therefore, the 5 milliseconds, the last one can be ignored. Yes. Alan, Asim, Gaurav, Isha, Michelle, Saran, Shilpa, Soris, SP, TJ. So Shilpa's point is, what was the last 5 seconds? So if you see what Soris has written, it says n into 20 plus 5. What does it mean? Meaning, by the end of 80th second, you see, by the end of 80th second, we have finished reading all of these. That means 4 into 20 milliseconds, right? That's 80. But the fourth one is yet to be processed, the last one, correct? The last one is yet to be resized. And that extra 5 milliseconds will go into that, right? So if there are n pictures, n into 20 will be this time, and 5 more milliseconds will be taken in processing the last one. Okay? Yes? And that 5 millisecond we can comfortably ignore, right? If there are million files. Good, good. So is it clear to everyone? Does it feel good? All right. So even if there is a single processor, we are able to actually reduce the overall time by 20%, right? Just by parallelizing. Earlier it was 25 million milliseconds, and then we made it by parallelizing it, it became 20 million milliseconds. Okay? It's a huge difference, right? So it's approximately 5.6 hours to resize 1 million pictures. It'll be 5.6 hours. Good, right? So what we understand from this example, that it's very clear that the main time has gone in reading the data from the disk. Okay, the main time has gone in reading data from the disk, not in the actual processing. Okay, so let me see. Asim is saying, did we miss something? If it takes 20 milliseconds to read the pic and 5 milliseconds to resize, so it'll be 10 to the power 6 into 20 milliseconds, which means 20,000 seconds, and which is 5.6 hours, right? 1 million pictures into 20 milliseconds. We're ignoring the remaining 5 milliseconds, okay? And then we got 20,000 seconds here, right? Milliseconds is 10 to the power minus 3. So it'll be 20,000 seconds divided by 3600 and these many hours, right? So these many seconds are these many hours, right? So it'll be 5.6 hours plus 5 milliseconds, correct? That we can ignore. Does it make sense to all of you? Plus 5 milliseconds for 1 millionth pic. Yes. Yes. The last one. All right, wonderful, wonderful set of answers. And all right, I would request everybody to pour in their opinion because there could be situation where I could miss things. Michelle's point is it only in the example that we are taking this kind of case where loading is taking so much time while processing is taking less time? Mostly, you'll be surprised to know that mostly it's the reading that takes the maximum amount of time, right? Processing sometimes take more time. For example, if you are doing the processing on in terms of say complex processing like graph processing or doing some kind of machine learning, in those cases, the processing might take a little bit more time. While is the main time goes in reading from the disk, okay? And you'll be amazed at the speed of your laptop if you remove the hard disk and put the solid state drive. Suddenly, your computer will become faster, okay? So now, my next question to all of you is, can this be improved if we buy a multi-core computer? Can we improve this processing if we buy really fast processor? But can this be improved if we buy really fast disk? Yes. So basically, in most of the processing that we encounter, it is the disk that is the bottleneck. It is the disk that is the bottleneck. And this is the classic example what I have given you. This is something people don't seem to give while talking about big data, but this is a classic example of comparing the 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 processing to the loading time. And 5 milliseconds is too high, by the way. 5 milliseconds to process the data is really high, okay? Reading will take actually more time, all right? So what we have established just now is that even if we keep on increasing the CPU, the chances are we are not going to get better speed, right? We are not going to get better speed. But if we are able to somehow make the reading from disk really faster, one way is buying an expensive hard disk. Other way is we use multiple computers. Out of 1 million picks, if we have 100 computers, we could put 10,000 in one, 10,000 in another, and so on, right? And then let it happen parallelly, correct? So the way we described HDFS yesterday, that HDFS is nothing but a distributed file system in which the storage of multiple computers are used. So if we take 10,000 of such pictures and put it on hundreds of computers, then suddenly overall time will be reduced to 1%, correct? Overall time will be reduced to how much? 200 seconds, right? Which is around a minute. If you have 100 computers and we could distribute our images to these 100 computers and such that every machine has 10,000 pictures, all of it could happen in parallel on these 100 computers, and we will be able to finish it in 200 seconds. Yes, sorry, that's right. All right. Does it make sense to you? This is where so Silpa's point is, as we discussed yesterday, that some of the images are backed up on other machines, right? So does the time count? Actually, that's even better. As we'll see further, let's say there is a particular block in which is kept on another machine. It actually makes this data available on multiple machines. So if one machine is doing something else, we can use some other machine for processing, right? If one machine on which our data was there, if that one is busy, we could use some other. Because our assumption at this time is the data is already copied onto HDFS. The data is already on HDFS. That's what our assumption is. Okay? And that assumption is not wrong, because the concept of data lake concept is that let there be a place on which we keep the entire data, entire archival of all the files, right? That's where the HDFS becomes the data lake for most of the organizations. All right, so let's try to understand how will we make this kind of processing happen on MapReduce. Let's say we want to do similar processing using many computers simultaneously. Instead of one computer, we're going to use multiple computers. Okay. All right. All right. Before jumping into yarn, let's go back into the history a bit and try to understand the primitive version of yarn. We used to call it MapReduce 1.0. In MapReduce 1, what happened was it was standard master-slave system. There was something called job tracker, and there were many task trackers. Task trackers and job trackers are services, or were services. Okay, what does it mean? They are basically programs running in the background doing their job, right? Job tracker, although the diagram shows that job tracker is installed on parallel to namenode, but it's not so. While task trackers are generally installed on the same machine on which data node is installed. Okay, so task tracker and data node go hand in hand together, while name node and job tracker could be elsewhere. Yes. Okay, so job tracker and admin node may not be on the same machine. All right, so the way in HDFS we have admin node and data node. That's right, Silpa. And the job tracker and task tracker are similarly a master slave model. Job tracker listens to the user, takes the work, divides the work to task trackers, and whatever is the result, it is saved in the disk. Okay, so these task trackers are running near to the data. Okay, so they generally take care of processing the data already on that data node. Okay, is the diagram clear? No? You want me to repeat something? So we have job tracker and we have task tracker. Job tracker takes the orders from you, and task trackers do the actual execution work. So you ask job tracker to do something, and then job tracker would hand over to task tracker will start working, and then if one of the task tracker fails, it will assign the same work to another task tracker having the same data. Okay, so the intention would be to execute the logic nearer to the data. A question from Shilpa. Does job tracker contains configuration detail of task trackers? Yes. Job tracker knows who are the task trackers, their IP addresses, their ports, and everything. Right? Good question. Keep going. Yes. A very good question from Michelle. What kind of task does job tracker and task tracker do? This MapReduce 1.0 could only do the task of MapReduce programs. Okay, we will create something called MapReduce program. We'll write map function, reduce function, and hand over to this framework, and it'll do that kind of tasks. Internally, it will order the data, it'll process the data, it'll then once it is done, shuffle the data and send it back to job tracker. Okay, so that's exactly the question that Michelle has asked. That's exactly the problem was with MapReduce 1.0, that it could only perform the workload of type MapReduce, right? It could only do MapReduce kind of workload. But since we have a cluster, it can be utilized in many ways, right? And not everything, like for example, I want to run my database or using so many computers. I could not do that. Or I would like to say run a streaming engine uh, and process the data using so many machines. That I could not do. So MapReduce had its own limitations. Therefore, this framework was limited. No, we are not using this framework anymore because of its limitations. Good question, sorry. I'm going to take that next level. So in Hadoop 1.0, it was doing too many things. It was the MapReduce was both the things. It was taking care of uh, assigning tasks to machines, and it was also doing the actual MapReduce logic, right? MapReduce logic plus actual execution, both were being done as part of MapReduce 1.0, right? So what was happening is it was basically a monolith architecture. It was a monolith architecture, as in it was doing both the things together, and therefore it was limited, right? So that's one of the biggest things in past that was done in Hadoop, that the MapReduce was broken into two layers. One, the kind of operating system layer that we call yarn. It takes care of cluster resource management, as in yarn can actually execute any kind of workload, while specific workloads such as MapReduce, other things, can use yarn for scheduling the tasks on the cluster. Okay, is the idea clear to you? So MapReduce 1.0 became yarn plus MapReduce 2.0, right? So MapReduce 1 became MapReduce 2 plus yarn. This refactoring was done, and because of this refactoring, as of today, there are many parallel computing engines like MapReduce. Okay, like we have similar to MapReduce, we have Taze, which basically is used in Pig. Then we have HBase and Storm and S4. We have Giraffe. We have Spark. We have OpenMPI, and so on. There are many more individual compute engines, right, on top of Yarn. Making it's like earlier, if you buy game console, you could only run games on it, correct? But if you buy a PC, you can install anything in it, and then they can be run on that PC. In the same way, on Yarn, you could run many kind of things. And if you don't like any of the existing frameworks, any of the existing workload executors, we can create our own application on top of Yarn. So Silpa's point is, what is HDFS2? Yesterday we talked about the total redundant, the architecture in which there was standby name node, right? That architecture in which it utilized Zookeeper, that is what was a big upgrade in HDFS2. Okay. All right. So now, is this clear to everyone? That there was MapReduce 1 in which only work could be done was MapReduce and not other kind of work, right? All right, wonderful. So Yarn supports all kinds of workloads, including MapReduce, right? Yarn gives you the ability to scale, meaning same computers, some of them are busy for MapReduce while rest of them are free, so they can be utilized. Yarn was compatible with older MapReduce logic, so people who wrote MapReduce programs could run on the newer version of Yarn, newer version of Hadoop. They did not have to make any modification. They just basically recompiled their program and shipped it again for Yarn. Okay, it improved the cluster utilization, it improved the agility, and since MapReduce was batch oriented, it gave space for other real-time systems. Now, you may ask that what became job tracker and what became task tracker? There is no one-on-one mapping. There is no one-to-one mapping. Job tracker became resource manager, application master, and timeline server, while task tracker became node manager. And slot in which the task used to get executed became container here. Okay, should we move to the next one? Gaurav's point is, could you go over the batch oriented program again? All right, let me explain. This is something which is very important for all. So a program that we run and it does the work in the background, and once it is done, it saves the result somewhere. That's called batch oriented programs. That's a batch, right? And what's the other kind of programs? Other kind of programs are which keep running all the time. For example, let's say you're processing all the data that's coming from Twitter, right? So you would like to run such program 24/7. Such programs are called streaming programs or stream processors. Such programs are not batch oriented. Such programs do not end. Such programs just wait until the new data comes. So there is a batch oriented one in which we start, it does the work and finishes and saves the result somewhere. And then there are other programs. For example, a database which runs 24/7, right? It's not really a batch process. It doesn't finish. Similarly, there is a streaming engine, a stream processing program. They don't finish. They keep running 24/7. All right? Does it make sense to you? So question from SP, is Yarn replacement of MapReduce? Not really. right? MapReduce runs on top of, yeah, MapReduce 2, MapReduce 2 runs on top of Yarn. Okay, so you can say that the Yarn plus MapReduce 2 was a replacement for MapReduce 1. All right. Okay, so MapReduce 1 becomes MapReduce 2 plus Yarn. All right. So older one was broken into two parts. We call it refactoring in computing, and and that's a Yarn. All right. It's a very important question that we need to understand. Um, the how does Yarn works, right? How does Yarn works? Including MR, Gaurav? Good question. So Yarn can handle all kinds of workloads, including MR, Spark, and everything, right? Spark is a replacement of MR, okay? So we will talk about these things in more details. Okay, good question. Let's try to understand the architecture of Yarn, all right? So did I answer your question, Gaurav? Not yet. We just touched very basics on Spark. The Spark is a computing engine, just like MapReduce, and both are kind of similar in the logic, just that Spark is a little faster. Okay. We also touched back on basics of Spark ecosystem. All right. Good. Good. So let's try to understand the architecture of Yarn. Just like HDFS, Yarn is also used by most of the computing engines. And this knowledge is very useful because what we are learning is various kind of distributed architectures. First, we learned the architecture of Zookeeper, in which there were elections and there were replications and there was this model of computing, right? Then we learned about HDFS, in which we were storing files, breaking into parts and replicating each part onto the disk, right? Now, third distributed architecture is Yarn. And here what you see is there are four computers, right? Four machines, or you can say each machine is running a service. So there are these services that are running. First one is running resource manager. Okay, so we can call it resource manager, first one. Second one is node manager. Third one is another node manager. Fourth one is another node manager. These are the services that are running in the background. Okay, so resource manager is single, as in single entity. It's a master here. Client talks to the resource manager. Resource manager is a component of Yarn. Node manager is also a component of Yarn. Node manager is installed on all the computers on which you want to run something. Okay, on which you want to run something. And the way node manager runs something is in the form of a container. A container, right? When you want to run something, things are run inside container. Okay, there's a special kind of container. There's a special kind of program that runs is called application master. Application master is kind of an entry point for your application. Okay, so the client comes to resource manager, and resource manager, the first thing resource manager does is create application master. That's the representative of the client. And then application master communicates with resource manager, negotiates with node managers, and get their work done by creating more and more containers. So container is the smallest executor unit. Container executes your container executes your logic, right? on, there are many containers for a single program. Okay, so container is like a what? Container is like a Java virtual machine, which is running there, and so on. Okay, so container is like a process which is running and getting your work done. Container enforces the boundaries so that you cannot, the program cannot misbehave. Okay, there could be multiple containers on a machine. Okay, so what's exactly the difference between node managers and containers? Node manager is a service, while containers are created by node managers on the machine to get the work done. Once the work of container is over, container is deleted and resources are reclaimed. Okay. Question from Gaurav. What is the role of application manager? We will come back to this. I think the best is yes. So it's not necessary. Good point. Good point, Isha. It's not necessary to have app master. Okay. A question from SP. Does node manager manipulate the service on a specific node? Yes. Node manager is the responsible component, is the one who is responsible for the node. Okay. Application master is the entry point. We'll come back to it in a minute. All right. Now, so we'll go into more and more details, Gaurav. Let me explain some more things. So node manager is one per node, while resource manager is, it's a central agent, singular one. So when we say yarn quickly, when I say yarn, the thing that should strike you is resource manager, right? That's the single point. That one knows its node manager. We will be interacting with basically resource manager. So node manager is responsible for the node. Okay, it's installed per machine. Okay, and generally node manager is installed on the same machines in which we installed data nodes, right? So that it can execute the logic nearer to the data. All right. So node manager is basically manages and enforces node resource allocations. Application master is per application. Okay. For MapReduce, there would be one mechanism. For Spark, there'll be one mechanism of execution, and so on. There has to be a special logic which will do the creation of container and execution of the logic and then get back, right? The entry point for every application is application master. It manages the application life cycle. It takes care of task scheduling. For example, MapReduce application master or Spark application master. Because of the, by virtue of this component called application master, right? The whole logic, because of that particular component, we are able to run any kind of workload on top of Yarn, right? So if you are creating your own program, which is competitor of MapReduce Spark, so what you will have to do is you have to create your own logic of application master. Okay, that's the entry point. That's the driver of the entire game. Question from Isha is, why is there no application master in LastPass? It just so happens that there has been only two applications, two clients. Therefore, there is no need of one more application master. Okay. All right, Shilpa, that's what I'm coming to. A question which people ask here is, what is the role of a container? Okay. The role of the container is running the process. It's a process which runs something. It runs the client's workload and enforces the security on client's processes. Okay, such as memory consumption should not go beyond certain amount, resource access should be restricted, and so on, right? A question from TJ, is there one application master per instance of a job or one for all instances? Is it a daemon process? Very good question, TJ. So there are two kinds of applications. One is long running and other is per job. So every program can create their own version of things. Okay, there could be three things, right? Three things, correct? First, you executed things and application master got created, and once the process was done, application master was done. Second is you created the application master once and it keeps on running 24/7. Third is the application master is a long running process unless we basically can run multiple workloads in a single application master, like running a Spark console. Okay, we'll come back to that, TJ. Very good question. Very good question. And a question from Asim. Service is something that runs in background to accomplish logic program. Yes. A question further is, so why is it necessary for node manager to create container to execute the logic? Right. So node manager is a service which keeps on running in background. And when somebody asks node manager to do something, instead of it doing it, it'll create containers in which it'll execute the customer's logic. Now, why do we need container is because container enforces security on client processes. There's a memory consumption constraints, resource access constraint, and so on. Do I make sense, Asim? All right, Gaurav, let me answer your question. Okay, so the client submits the application, right? And resource manager launches the application master inside the container. Okay, so what happened was after talking to node manager, resource manager launched the entry point of your program. If you are launching MapReduce, so first of all, MapReduce framework has to launch, right? So the first thing resource manager will do is it will launch MapReduce framework inside application master, right? And then the application master of MapReduce will register with RM, and then client can connect to it. Why? So that it can see the progress. Afterwards, application master does some analysis, and based on that analysis, it requests resource manager for further containers. Okay, so you can see that application master is behaving like a Trojan, or is behaving like a head office who does everything on behalf of client. Okay, and then resource manager allocates the containers, and node manager launches these containers in these apps in the containers. Okay, and node manager talks back to resource manager about resource usage. Client can directly talk to the application master for understanding the status, and then client talks to application master for status. Okay, so client basically can talk to application master, and application master can expose a service uh, as long as it's running. Once it's done, application master deregisters itself from resource manager and shuts down, and all the containers are delocated. All right. A better example to understand the whole process would be that if we think of client as Microsoft or any other organization such as Shell. Okay, please pay attention. So imagine that the whole yarn was like a country, and resource manager is like a president. Okay, and then there are states. Every node is represented like a state. So here there are three states: state 1, 2, and 3, right? This one is California, this one is something else, this one is something else. Okay, and I think this one is where is head office of Redmond? Seattle, Redmond. I think it's Washington, probably. Okay, and this one is something else. All right. So there are three states here in the diagram: the state 1, state 2, and state 3. Node manager is like the governor of the state. Okay, and resource manager is the president, and clients are Microsoft and clients are Shell. And what do they want to do? They want to get their work done. And how do they get their work done? By establishing offices, right? The Shell would have to open its office and get the work done there. Microsoft will open its office and get the work done there, right? And if, let's say, both Microsoft and Shell will have some location constraints. Like, we would like to open, some of them will say, we would like to open our offices near the sea, right? If there's a company called Schlumberger, they would like to open the offices near the sea. That's the resource constraints from their side, right? So clients such as Microsoft goes to president and says, hey, we would like our offices to be established. Okay, president will say that let's do it this way, that instead of you going through me every time, or instead of you seeking visa every time to come to our country in order to discuss, why don't you establish a head office? Head office, you can see this is the head office for Microsoft. Application master is like the head office. Next time, all the requests or the application forms that will come to president or states would come from the head office, right? So application master is the head office. It is the representative of what client wants to do, all right? Then further, the head office of Microsoft will send a request to president saying, thank you for establishing our head office or helping us establish head office. We need to open three more offices in the country. One we need in the say say here. Okay, one we need to open in this state. Other we need to two other we need to open in the other state, right? So application master will request president, the resource manager, and then resource manager will talk to node managers, meaning president will talk to governors that could you give these many offices to Microsoft and run the offices. And then Microsoft will will get the approval from governors and they will create their offices, right? Now, what is the container? Container means the legal entity of an office, right? Like, for example, in an office, you're not allowed to do certain things. There is certain environment clearance and other things. Those restrictions apply on all offices. In the same way, node manager creates containers, and these containers enforce the resource restrictions. They cannot do something other than what is allowed. All right, is the diagram clear to all? All right, Shilpa says that replace Obama with Trump. Yeah, I think I'll stick with the old one and I'll have an excuse that I don't want to. Okay. And I'll have excuse that it's hard to change these diagrams. So it is on the so question from SP is, so it's only first time that the client establishes relationship with resource manager. Yes. So it's only the first time the client comes to president or the resource manager and establishes the application master. And afterwards, everything is done by the application master on behalf of client. Okay, Isa's question is, so what happens to the container after execution is complete? After the execution is done, the container is delocated. Okay, it should be made available. The same resources should be made available to another processes. Okay, wonderful, wonderful set of questions. Yes, RM is like a true manager, delegates everything even to further layer of managers and apparently does nothing. It connects the client to the application master that if you want to see the status, ask your application master, not me. Okay, so remember this part here. AM registers with RM. Application master registers with RM and client can seek the status directly from AM. All right. So yes. So we can actually take the same analogy with the corporate structure, but I found that this one was easier and more sensible to us. Okay. A question from Gaurav. AM is ephemeral then, or are there other kinds of AM? So some of the AMs actually are long running, right? I'll explain to that. Some of the AM application masters are actually long running. They run forever. SP's question is, but creation of containers are more controlled by application master. So request is started by my application masters, and sometimes client upfront can also tell that I would need these many containers to begin with. Okay, good questions, very good questions. All right. So these two questions are very important here. One is, are there any other kinds of application masters? And second is, uh, the creation of controller is done by only the client, or can it be done by client also, or only by application master? These two things we'll cover quickly. Question from Isha is, so is there a limit on how many containers can be created? Okay, so is there a limit on how many containers can be created? That's based on configuration, and that's yes, that's right. There is a limit on containers. So while creating adding our node, we generally define in the yarns configuration that how many containers are allowed on each machine. Okay, good questions. Question from all right. No worries, Saran. It was just a joke, I understand. All right. A question from Sorry is there a limit on how many node managers can be there? It's up to us. If we have 100 nodes, ideally we should just put 100 node managers. Just that I would not like to execute anything on machine that is designated as resource manager. Okay, so out of 100 nodes, I'll dedicate one to resource manager, rest to node managers. Wherever there is a data node, I'll put node managers. All right, wonderful, wonderful. Okay, Yes. So now let me answer Gaurav's question, and there was SP's question also. Okay. The client, when they start the communication with the yarn, they send a resource request. Okay, they send a resource request. Similarly, application master at the later point sends a resource request. What does resource request contain? It contains how many containers do we want, and for each container what kind of memory we are talking about, and for each container what kind of CPU. Do we need multiple CPU, single CPU, or where is this container located? Do we want these containers to be near to our particular data? That is also part of the resource request. While sending out a request to Yarn, we can tell how many machines do we want, meaning how many containers, how many CPU, what kind of memory, and most importantly, the locality constraint. Do we want these containers near to this particular data? If we have a file which is of terabyte size, which means 8,000 blocks, right? So we might ask for, say, 1,000 nodes closer to this particular file, right? Out of those blocks, wherever they are available. Okay, so here the important point is that while sending out a request, whether the client or the application master, they can specify all of these details, and they can either say upfront that we need it now, or they could also say that we will let you know as we go. Okay, the second question is, what does it mean by when do these containers or application masters are delocated? That's called application lifespan. Application lifespan can vary too dramatically. Okay, generally the lifespan of an application is categorized into three categories, right? First one is, the simplest case is one application per job. Okay, one application per job. That's MapReduce, meaning we submit our job, and it launches the MapReduce, finishes it, and then once it is done, it saves the data somewhere, and that's all. That's one application per user, right? Whenever you want to do something, it is going to create one application master. Okay, for every MapReduce job, whether I'm executing twice or you are executing multiple times, for each execution, there will be one application master. Okay, second kind of load is one application per workflow or user session. One application per workflow or user session. Okay, meaning okay, what does it mean? One application per workflow or user session? Basically, there is a session like Python. How many of you have used Python? Quickly. Okay. So if you can see here, when I start, say, Python, right? Okay. So here it starts a console. It starts a console. In the similar way, when we start, say, Spark, okay, we are starting a Spark shell right now. Okay. So it's basically starting an interactive shell. Okay, so using the command Spark Shell, we just started a Spark Shell. Now what you see here is it's going to present us a prompt on which we can type our commands, right? So we do something, it evaluates it and waits for more commands. Okay, this is called REPL. REPL. This is read, evaluate, process, loop. Okay, it keeps on asking us for input, and and we can keep on giving it input, and you can see that we are defining where x equals 4, and then we are saying x plus 5. So you can see that we are asking it questions and it is going on, right? It's a session. There is a session involved because whatever we defined x earlier, it is available even now, correct? Right. So what I'm trying to show is that this Spark Spark Shell is per user session, meaning we are doing multiple things, but in the same session. It's in the same session, right? So that's the difference between MapReduce is like you submit it, it'll do the job and then return the value. While Spark is interactive session in which user can get multiple things done, right? For these kind of jobs, it will take a little longer. It'll run it for longer, right? And third one is a really long running application like a database which keeps running all the time. So there are three kinds of application lifespans. One, submit and then forget, like use and throw. Other is there's a user session. Multiple workloads can be executed in a single session. Third one is a long running application, such as a database, and database kind of applications can be easily created using Apache Slider or Impala. All right, is it good? All right. Sometimes mm, people ask like we would, yeah. Slider is more like creating another. If you want to run something in the background forever, then you can use Apache Slider. Okay, it's basically a wrapper. It's not a DB. Got it? All right. Sometimes we may want to create our own yarn application like MapReduce, HBase, and so on. We would like to create our own application. So what we have understood is when we are creating our own application, one thing which we have to build is application master who will talk to yarn, send the resource request, and also give that this is the program that needs to be run inside container and so on. Okay, so it's fairly difficult work to build a yarn application. Okay, so my suggestion would be to first try to use existing frameworks such as MapReduce, Spark, etc. Second, try to utilize existing tools to build jobs. For example, Apache Slider, it basically runs existing applications into distributed way. Okay, and Apache Twill, it's a Java, it makes any Java runnable run on yarn. Okay, anything that can run you with Java can be run on yarn. All right, otherwise if you're not ready to use either Slider or Twill and do not want to use MapReduce, Spark, and other frameworks, and still you are adamant on building your own yarn application, my suggestion would be that building from scratch is complex. So use Yarn's project that is bundled as an example with Yarn, and it's called distributed shell application. Okay, it's called distributed. All right, so you can take a look at here. So this is the example where they have written a logic of what goes in application master and so on. Okay, so that kind of example is good. All right, let me just link it here. Okay, so is everybody comfortable so far with Yarn? A question from Saris, can we download the slides so that we can save them in your laptop drives or print? Yes, yes, feel free to download. Okay, so how do you download? Okay, go to my courses. Okay, some of us are a little confused with respect to the courses. So here you see multiple courses. This one contains the live training recordings. This one contains the entire content for the course. Okay, well organized with exercises. Okay, so here what you see is it has Yarn, for example, right? So you can simply go to jump to resources here. All right, see that? And there you can open it in a new window. Okay, and then you can download it, or you can just simply say print. There should be a print somewhere. Okay, it should be here. All right, so here you can just simply download or print. Is it clear to everyone? All right, in the my courses tab, the third one contains the recordings. You could open it and then see the general things here. And we have first recording and other recordings. You see, these till here we are done. Okay, I'll be adding from 6th session onwards. Okay, so this is about the overview of this. All right, so coming back to it, so that was about Yarn. Any questions at this point? Yes, we are covering Scoop. Okay. And I would recommend if you want to really, learn Scoop and Flume, I would say that the self-paced ones are far better here. Okay. All of whatever we are discussing, I have already recorded it separately, and it's available here, most of it. Okay, let's start. Any other questions at this point? Feel free to ask questions. There's no hurry. Okay, there's no hurry, and we can anyway cover the entire course, no worries. And even if we have to take extra classes, so do not worry about uh, you know mm, delay or any other things. Okay, we are we have enough time. All right, so let's focus more on not more on asking questions and understanding concepts. Okay, that's the most important aspect. All right, so there is nothing much with respect to Yarn. The only thing I would like to show you is maybe all right, so I would like to show you that using Yarn command. Okay, there's a command called Yarn, and with this Yarn command we could see the how busy is the cluster. Okay, so you can see that uh, there is one application running and 3,863 have been submitted and 3,821 have been completed, 26 killed, 15 failed. Okay, And the memory is this much available from all the clusters and so on, right? This is the uh, this is the task that's running yet. Okay. And other commands, if you just type yarn command, you will see the the other arguments to yarn. Okay. So you could say yarn followed by any of these commands, and it will show you the list of the result. Okay. So you could say yarn application. Okay. It shows uh, other further things. So these are the applications as of now being run on top of yarn. You see that? So mostly, I would strongly suggest everyone that to get very familiar with the Linux, because most of the interfaces for these tools do not have a UI version. Although there is a UI version, I'll show you. There is a UI version, but that's very rudimentary. It's not as sophisticated. Okay, I'll show you. If I go to, say, here and click on Ambari, just Shilpa, just type yarn command and you will see all the list. Okay, let me log in to admin. Okay, although I can log in into my account as well. All right, but yeah, I just want to show you that sometimes you may want to use yarn here. So here it shows you that all of these processes are running, and one process that we have not covered in this discussion is application time server. Application time server kind of tracks the application timeline and just records the time taken by each application. All right, and here, so you can see there is something we can restart the yarn. There's a resource manager launched. There's a node manager started, and so on. And you can see the the client memory utilized. Okay. So how can I launch command line window we just launched? Go to my lab, log into CloudX Lab, click on my lab, and you will see these login password. Click on Web Console. All right. Great. All right. So here you can just type yarn and it will show you all the possible commands, right? Out of this, most useful is yarn application. Okay. So you could say list, and it'll show you the list of all applications. See? All right. Yeah, this is Web Console. Okay. All right. So let's take a break for 10 minutes and we'll start at 9:41. All right. Okay. And all right. So if it is only for today, then we can get 15 minutes break, but I think let's just take the 10 minutes break. All right. Sorry, can we do that after the break? All right, everyone, I'm back. Should we start now? All right. So Saris is facing a little bit problem. Let me take a look. Yes, Saris, please go ahead and share your screen. Let me stop sharing. Yes, please go ahead, Saris. What exactly is the problem, Saris? Hello, are you able to share? Ouch, looks like he has exited. Never mind. I think he'll be joining or something like that. All right, never mind. So for now, okay. Any other question before we start with our MapReduce discussion? Okay. Sorry, just wait a second. I will stop sharing and then you can share. Yeah, please go ahead. Yeah. Can you go back? Can you go back, please? So here you clicked on this. This is fine. Okay. And I will say that maybe something wrong with this. Go back to a PDF again. The second tab. The second tab. Okay. Yeah. And you can click on download. What happens when we click on download? Um, it's not redirecting properly. Maybe the browser is try again. Try again. Press shift refresh. Yes, download. Shift refresh. Yeah, shift. I think there's something wrong with your browser. Try Chrome probably. Just do one thing. Just click on this. Copy the URL. Just copy the URL only. Okay. Copy the URL and yeah, and just open it in Chrome or any other browser. Not IE, some other. Say Chrome. Open it in Chrome. Enter. Okay, close that. And is there download button available or something? All right, refresh it. Okay, I'll tell you something. You go back to the IE again. Go back to IE again. The one which was open. The one which was open. Not this one. Where were you there earlier? Yeah, this one, right? Just right click on download. Right click on download and say copy link. Is there a copy link option somewhere? Oh, it's not there. Okay, okay. Can you click on save page as? Just click on download, right click on download. Yeah, save page. Okay. Does it give you an option? Yeah, yeah, try that. Yeah. No, actually, it's saving as HTML. Cancel it. Cancel it. Or what is this open with Lumen PDF? In the top, do you see open with Lumen PDF? Yeah, this one. Click on that. Oh, click on Lumen. Yeah, let's see what happens then. The files. Okay, what does it say then? Open my file. What does it say? It's asking for, you'll have to select an account. So basically there's some problem with is there on this machine. Otherwise it comes pretty well. Or maybe if you just sign in Google Chrome, everything will come up. Go to Google Chrome window. There you can simply sign in and things will come out well. Okay. Go to Chrome. It's already open there, and it's asking me to. Or you can save it to your Google Drive, and from there you can anytime access. All right. Okay. Why I don't want to send you an email is actually why, because these slides basically keep on getting updated. Okay. And that's why I want to keep them in Google Drive. Okay. Just click on sign in and it should be able to. Just click on sign in and sign into the account and you should be able to do that. Okay. Uh, okay. Advanced and everything. Okay. All right. There's something wrong. I think even if I send you PDF, I'm not sure you'll be able to access those. But nevertheless, I'll just send you the link to the folder and then we'll see. Okay. All right. We'll share. Okay. I'll ask somebody to share with you. All right. Okay. Okay. All right. So I'll ask somebody to send you the PDFs and all right. So can you see my screen? All right. Any questions before we move forward in MapReduce? No questions? Okay. So what we're going to discuss is we are going to start from scratch, as in the basics of programming, and try to solve a simple problem. And we will try all possible ways, and then we will logically deduce that MapReduce is and was a good solution. All right. So let's start. First of all, let's try to understand the what does it mean by sorting. Okay. So let me ask you a very simple question. Let me ask you a very simple question. How fast can 1 gigahertz processor sort 1 terabyte data? This data is made up of 10 billion 100 byte sized strings. You have got 10 billion strings, which are each 100 characters. So you want to sort such data. Sort means ordering. How much time do you think it'll take? Yes? Anybody? Any guess? Alan, Asim, Gaurav, Isha, Saran, Shilpa, Saris, SP, TJ. Any guess? Like Michelle has to leave early today, right? So yeah. Yes, you just so here what we're trying to do is I just want to see your random guess. How much can you guess? And how would you generally do the computation like this? Saran's question is big O notation. Actually, big O notation is something which is very hard to do in this case because big O notation would generally tell you the order, the magnitude, but it will not tell you uh, the the time in seconds or minutes. Yeah, but that's a good approach. So yeah, go ahead. I mean, do a approximation. It's an approximation game. Just back of the envelope calculation. Yes. A 1 byte size string means one character, like S of Silpa, for example. 100 byte means 100 characters. All right. Just give me a number. It'll take 1 hour, 10 hours, 20 hours. Even if you are 100% wrong. 100% wrong means you are guessing double. Okay. If your guess is 100% off, that's also okay. All right. It takes somewhere between 6 to 10 hours, right? For some computers which have faster hard disks, it might take 6 hours. For slower hard disks, it will take 10 hours. But here also, the main thing would be the time taken to read the data from the disk. There is no calculation as such here. This is based on some experience. All right. And now, what is wrong with 6 to 10 hours for sorting data? One, we need faster sorting. Let's say we need to get the work done in a faster time. Often we need to get our work done less than 10 hours, right? And sometimes we may need to order bigger data. Sometimes we may need to sort bigger data, right? And we might have to do it more often. Therefore, 6 to 10 hours is not good enough, right? Or are you happy with 6 to 10 hours? If you have to order 1 terabyte of data like this, sort 1 terabyte of data, are you happy with 6 to 10 hours? Right? Because you might need to get it done faster and do it sorting bigger data. If the data grows to 2 terabyte tomorrow, it'll actually be more than more than what we imagine. It might become around 12 times, right? If data doubles, because it's not linear, it's n log n, right? 10 billion means 10 to the power 7, and then 7 into 2 into, which is 14 times. So if data becomes 2 terabyte, the overall time that is taken would become 15 times probably. Okay, so say for example, Google was able to sort 10 petabyte data in just 6.5 hours in 2011 using 8,000 computers. Okay, using 8,000 computers, they were able to sort 10,000 times data in 6.5 hours. Right? So they were able to achieve this. Using a single computer, this is actually not possible, right? This is not actually possible, that because it'll take around, for us, it'll take around 60,000 hours, right? So, okay, so Arishi's question is, how are you getting 15 times again? You can do n log n, okay? Just quickly, I was doing off the envelope, okay? I was just trying to use a formula for that, all right? N log n, as in, there are, how many records are there in this one? There are 10 billion records, right? And so if you put n into this, then you can compute, right? So if you say 20 billion log 20 billion divided by 10 log 10 billion, you'll get the answer, right? So, all right, I'm just guessing, I may be wrong. The 50, it may not be 15 times, all right? Don't, I mean, that number could be different. Okay. Now, so Google was able to do 10 petabyte data sorting using 8,000 computers. Now, why is sorting such a big deal? We have talked about sorting so much. Why is sorting such a big deal? Every SQL query is impacted by sorting in one way or another. Every SQL query is impacted by sorting. For example, where clause is impacted by sorting if we have indexes on a table, then where clause of SQL performs really well, right? So who is not aware about SQL, the where clause of SQL? Is there anybody? Alan, Asim, Gaurav, Isha, Saran, Shilpa, Soris, SP, TJ. Looks like everybody is aware of where clause of SQL. Good. So every SQL is impacted by sorting because, for example, where clause becomes very fast if the fields on which you are running where clause are indexed. And what is indexing? Under the hood, it's actually sorting. Okay, under the hood, it's actually sorting the data. Group by is heavily impacted by sorting because grouping essentially uh, is sorting, right? Because you order the data that brings same things together and then you group them. To group things together, you need to order the data and then group them, right? Joins. What is a join? We are taking one table of data and another table of data. Wherever the values are matching, we're bringing those records together. That's called joining. Joining is immensely enhanced if the sorting algorithm of database is great. So joining involves sorting. All right. If you have two tables and you're trying to join, taking one record and looking up on the other table is very slow. If you sort the data, that become joins become really, really fast, right? So most of the joins in these databases can be heavily impacted by sorting, right? Then order by is also impacted by sorting, right? Because that's actually the sorting. So sorting is a very, very important algorithm in data science. Not only SQL, but most of the other algorithms depend on sorting under the hood. Graph algorithms, or say PageRank algorithms, and all complex machine learning algorithms are one way or the another impacted by sorting algorithms. Okay, so sorting is a very basic algorithm and is actually the heart of the computer science. Okay, so that's why we are talking about sorting. Sorting is really a big deal. And you'll be surprised to know that MapReduce was just a big engine that could sort data. MapReduce was just a big engine that could sort data lying on HDFS. Okay, you can always think of MapReduce as a big engine that can order data lying in HDFS. Okay, and we'll see that why am I making such a statement. Okay, so MapReduce was basically a big sorting engine. So what is MapReduce? It's a paradigm. It's a programming paradigm to help you solve big data problems. specifically those jobs which are sorting intensive, or those jobs in which disk read is involved. For example, the first problem that we talked about, where we are reading data from the disk, right? So that's those kind of jobs, and those jobs in which sorting is needed are are very suitable for MapReduce. Okay. Generally, you will have to write two functions. One, mapper. Mapper prepares data for sorting, and Hadoop sorts the data. And once sorting is done, your reduce method does is called on the on the groups of values. Okay, so mapper prepares the data for Hadoop, and Hadoop's groups the data given by mapper based on the key specified by the mapper, and then after sorting, Hadoop groups the data based on the same key, and then it is sent to the reducer. Okay, reducer is executed by Hadoop, and then all right. So please note that we create two functions. One is called mapper, and other is called reducer. Mapper prepares key and value. Reducer brings multiple values into single, and these two functions are handed over to Hadoop. These two functions are handed over to Hadoop, and Hadoop does the processing for us. All right. MapReduce as a paradigm, as a concept, is also supported by many other systems, such as MongoDB, such as CouchDB, Cassandra, and in some way, Apache Spark. Mappers and reducers in Hadoop can be written in Java, can be written in Shell, Python, or any program. All right, we'll try all these possibilities. Okay, so let's try to understand how does it look. Just a second. So the title is wrong. All right. Okay, so what we have learned so far, there is Hadoop, there is HDFS. HDFS has HDFS blocks, which are, let's say, here there are 3 nodes. So 3 nodes are having HDFS blocks, right? And when we specify, when we call Hadoop MapReduce job, what we give, we tell Hadoop that this is the file that contains my data. This is my mapper logic, the logic that converts the raw data into key and value. And then another thing that we hand over to Hadoop is the reduce function, meaning how to combine multiple values together. You can think of MapReduce as a group by. Okay, like in group by clause of SQL, we specify on what basis the data need to be grouped, and then we specify on what basis multiple values for the same group be combined, right? So when we hand over these 3 things, one is the location of input data in HDFS, the mapper function, that reducer function, then MapReduce starts working. And what does it do inside? First of all, it will locate all the HDFS blocks for your file. Okay, and those HDFS blocks, either they're replicas or the actual block, doesn't matter. Whichever machines are free, it finds those machines near to your data. Yes. So question from Sorry, please repeat the group by relation to. So MapReduce is like group by clause of SQL, right? In group by, what all we do, we say select star from table, select group the field on which we have grouped the data, comma, sum of some value, from a particular table, and then we say group by particular column, and that's it, right? So what do we do in the group by clause in databases? We specify on what basis our data need to be grouped, right? We specify what table needs to be considered, right? And we specify how should the values for each group be combined, right? So we specify, similarly, in case of MapReduce, we specify the input data equivalent of the table, and we specify our mapper function that is specifies on what basis the data needs to be grouped, and then we specify our reducer function on the basis of which the data for each group be combined. Okay, and you'll be amazed to know that most of the problems can be solved by MapReduce. Okay, it's not mandatory to specify reduce function. Okay, in that case there will be no grouping, no sorting, only the conversion of the data from one form to another would happen. All right. All right, let's try to understand what happens. Kind of, yes. Not group by is not equal to mapper function, but the whole map reduce. Okay. So when we say the group by involves all the things, right? We group it, we aggregate it, and everything. So group by X is equal to saying that I want to group my data based on a particular field. Okay. All right. I will see more examples, and you'll get more clarity as we go ahead. All right. So let's say you have data here. These are, say you have three HDFS blocks for a file. Okay. That HDFS block will be translated by Hadoop into something called input split. Okay. Input split is a logical translation of data. You remember our HDFS blocks were raw and they were fixed width so that the boundaries, could be, let's say half of the line goes in one block, another goes in another block. That could happen. So those kind of raw blocks are converted into input split. Okay, input split. If it's a plain text file, input split will be bunch of lines and so on. We can specify on what basis the raw data from the HDFS blocks be converted into input splits. This is called input format. Using a specification called input format, we can tell Hadoop that how to translate our raw data into input split. Okay, that's the important part, and we'll talk about input format after a while again. So this input split basically is used for the on top of input split. Our mapper function is called. And then whatever mapper does, generally our mapper function would convert an input record into some key value. Okay, those key values are collected on each machines and sorted locally. Okay, so that the sorting work can also be distributed. Is it clear? So output of mapper is being ordered on the same machine. All right, because what does mapper supposed to give? Mapper is supposed to give a pair, key and value. For each record it could give multiple key values. For each record it may choose not to give any key value. It is up to our need. Whatever basis we have, if you want to group, let's say, some data based on last name or inverse of it or something else, that's what mapper specifies. Mapper gives out the criteria for sorting and the value. Okay, so Hadoop sorts that data based on that criteria specified by Mapper. Okay, Mapper, the blue colored one, is our code. This is our logic. This is our program. Sorry's question is, Sorry's question is that for stock price, I'll come back to it in a minute. Let me just compare this example. I would talk about these things in a little bit more details. All right. Now, once sorting is done on each machine, this sorted data is copied to another machine and then merged together. Okay. The sorting can be merged together on an external machine. Okay. We will come back to that, SP. Just give me a second. There are many input splits. There are input formats which can translate to any kind of input split. There are many ones, JSON format, in XML1, and so on. Okay, and I'll give you example in a minute. All right, once sorting is done, sorting and then grouping is done, then the merge happens, and for merge, your reduce function is called, and then the result is saved to HDFS. All right, so this is your application, this is your application. So and it's being executed by Hadoop, right? You did not decide that your mapper function will be called so many times on 3 different machines. Okay, mapper function is called on input split. Input split could contain many record. Against every record, mapper function is called. Okay, and your mapper function can generate as many key value as it wants, and then that result could be gathered somewhere on a third machine, fourth machine, and then merged. If your file was really big, let's say in case of Google, they were using 8,000 nodes, so there could be 8,000 nodes on which your mapper logic is running. There could be 8,000 machines on which mapper is running. Okay, so you can see that our discussion long back where we were trying to process images, right? So here the image processing could become distributed. All right, image processing could become distributed where each record, each input split is giving each record as image, and our mapper logic is just resizing those images, and there is no reducer logic. That means there is no need to sort or provide key value. We are just providing key for the namesake and nothing else, right? All right, so we can choose to have no reducer, so you can always think of MapReduce in terms of this. For example, let's say we want to make burger. So on mapper phases, each individual uh, data or each individual part is being sliced into something else, right? Each part is being processed parallelly, maybe on different workstations, and then they're being combined to form the burger, right? So mapper phase translate one to another while reduce combines them together. Okay, so this is our quick overview of MapReduce. All right, there'll be too many questions, I know, but again, why did we why did we come up with MapReduce? That's something I would like to discuss. A question from Shilpa: what are those 3 blocks on HDFS? So let's say your file is how much? Let's say your file is 300 megabytes. Okay, how many blocks will be there for 300 megabytes? 3, right? So these 3 blocks are what are being used here. All right. Yes. A question from Gaurav. The three blocks after the reducer turn into one block on HDFS. Very good point. So we are not really saving the data as such. Sometimes if there is no reduce phase here, this data would go directly into HDFS, which means there will be three blocks again. But here, since there's a summarization phase, since we are merging data, and therefore the there is one there is only small data left. A question from TJ is every block has one-on-one correspondence with input split. Very good question, TJ. So not always. Not always. Sometimes, let's say our input format is such that we would like to combine all of this data into one machine. Okay, in those cases, there could be a scenario where this data is getting transferred to a single machine to form a single input split. Okay, there are those scenarios also. So a question from sorry says, is size fixed for each block? Yes, HDFS size is fixed, just that last one is smaller than the 128 MB. And question is, input split, are the sizes same? Answer is no. It's more like logical entity. Let's say in each file, if one line is represented by a record, and an input split is an array of records, and so therefore input split cannot be equal. They could be approximately equal, right? Because every line could have different size. So the difference here is HDFS block is a exact same size, while split is based on what problem are we trying to solve. Let's say our HDFS blocks, the HDFS file is compressed in the zip format, meaning one third part is here, one third part is here, one third part is here. But if you want to compress zipped format, we would need all of these blocks on single machine, right? Therefore, there will be a single input split for all of this. All right. A question. All right. A question from Gaurav. From each HDFS block, the merge happens on a different machine. Does a sorting also happen there to sort fragments with respect to each other? Very good question, Gaurav. So yes. So here, sorting this data is already sorted. This is also sorted. This is also sorted, and then there is merge sort happening here, right? This data is being sorted in a way that we pick up the first record from all three, then compare those three and pick up the smallest one. And then from the row from which we pick the smallest one, we pick the next one, and then again compare and so on. Okay. So here again, there is a sorting, but it is actually pretty fast. Okay. It is actually order of n. All right. We will go into that detail again. Yeah, did I miss somebody's question here? There was a question from SP regarding split. Okay. So so Silpa's question is, so what all the users has to write code for mapper and reducer, right? Sometimes you already have a program that gives out some result. You can utilize that program as mapper and reducer. Okay. And user, since not many users are great with coding, so we may want to use Hive. Under the hood, every SQL that you write on Hive gets converted into MapReduce. All right. But it's important, even though you may never write a single MapReduce, it's important to understand the overall philosophy because the distributed computing is built around it. All right. Question from Shilpa is that built in HDFS by default? Hadoop by default runs on HDFS, though it can, because it's your code can read data from anywhere, right? Therefore, it can read data from anywhere. We have some examples of the code. All right, Shilpa. All right. So that's a quick overview of MapReduce. I want to now go back to the beginning and try to solve something with something without MapReduce. Okay? Is everybody with me? I think today Alan is not around. Asim is also not around. Shilpa, you have any questions for me? Yes, we'll talk about shuffle phase in a couple of minutes. Don't worry, sorry. Okay, we're going to go more detailed into MapReduce at a later point of time. This was just a quick overview so that we get a little, you know, cloudy, even if it's cloudy, you get an overview idea about MapReduce. Okay, shuffle phase is basically, if you want me to ask, shuffle phase is basically this. Okay, shuffle phase is basically this. All right. Now, a question to all of you. Let's say you have the plain text file containing hundreds of textbooks in plain text, as in you can open them in the notepad. Your task is to find the frequencies of words, as in find all the unique words and how many times each unique word has occurred. Yes, I'm not asking how to write MapReduce for it. If your boss asks today, or you have to find out by yourself, like what will you do? Okay, so Isha will use group by probably with the databases, right? Feel free to, come up with any kind of tool, kind of technique, a practical technique, okay? A practical solution. Maybe use Excel or maybe use Unix, maybe use something. So a practical one. I mean, it's like you go to office one fine day and your boss asks to do this. What is it that you will do? Okay. Okay, wonderful, wonderful set of questions, set of answers. Okay, let me read through each one. So I'm reading through, say, Isha's answer. Okay, Isha says that group same words. Okay, good. Sorry says scan the text for words and then count. Okay, using count command. Okay, and then select distinct from. Okay, okay. Saran says that maintain a counter outside and parallelly read the files and update the counter. Okay, okay. So counter is like a hash table, Saran. Okay, all right, right. So teacher, we are trying to do it without MapReduce. All right. How do we do in case of I mean, in our usual lives, if without Hadoop, if we have to do the same thing? There are many use cases of using frequencies of the words. There are many use cases. For example, um, in Amazon Books, there is a feature called See the Character Plot. Okay, whereby we see how character. It quickly shows that which character appears uh, on where in the book visually. Okay, and that basically is based on frequencies of the words. All right. Similarly, if you want to do analysis of a word, analysis of, let's say, circumstances of various decades. So what you can do is you can take newspaper, scan the entire newspaper, and then for each decade you can do the word frequency summarization, and you can see that the word frequency actually shows a lot about culture in that era. Okay. So for example, earlier in the days before independence in India in 1800s and 1900s, you'll find, say, uh, what do you say? The words like, what do you call? I forgot the words. Okay, so you can see that using word frequencies, you can analyze the a lot about the content. Isha says yes, in SQL, I'll first break the textbooks, then store in the timetable, okay, and do the count on words and group by them. Perfect. Yes, that's the one good logic. All right, wonderful, wonderful set of answers. Now let's try to see a couple of approaches what you have listed down. First, one approach is by Saran that, and some more other people, probably Sorry's also. Create a frequency table. It's called hash table, hash map, or a dictionary. What does it mean? It means that it is basically a data structure in which we store key and values, right? It's the data structure in which the data can be quickly retrieved based on the key, and we can update the values quickly based on a key. Okay, so it's that kind of dictionary. Like in a dictionary, we can quickly search for a word and its meaning, right? And similar is the case with hash table, hash map. So we start with creating this empty frequency table, and then we start reading the files one word at a time. If this word is already existing in the dictionary, we increase its frequency in the hash table. Otherwise, we create a new entry in the dictionary. All right. When no more words are left in the file, we print the hash table. Do you see any problems with it? Okay. So again, those who are familiar with Python code, this is how I'm going to do. Create a dictionary for each file, in each word in the file. I'm going to split each line and iterate over it. And then if the word not in the word count, then all right. if it is not existing in the table, I add it with the 0 count and increase its count, and so on. All right. And then I just, once everything is done, I just print the frequency. Is the logic clear? Is it clear to everyone? Yes, sorry. Yes, sorry. Please go ahead with your question. Okay. Okay, I'll just come back to Soris's question. But why do you want my access to my folder? All right, I think there's been some confusion. So what I was saying yesterday is you can access my folder, but it's not, I'm not sure if it is open for all. You can go to cd slash, it's on HDFS, my folder is open to all, probably. Okay. And but on locally it's not. All right. So maybe the thing that is of interest to you is the data folders. These are the data folders at the top level. Okay. All right. So anything, there is nothing, all the data sets, everything is common to all and is available either here or in the examples. All right. As we go forward, you will see that. All right. There is, I mean, absolutely nothing much here. All right, so you would not require any of the access to my folder. All right, if you get an error while accessing something, let me know. We will fix that part. Okay, so Shilpa, you want me to explain again? So we created an empty dictionary, meaning hash table, in which we can store key values. Then we started reading the file, and for each word in the file, what we are doing is we are checking if it exists already. If it is not existing, we are making an entry with the 0, and then if it is already existing, then we are just increasing it by 1. All right. And then once all the words are done, we just print the frequencies of this table. Okay. Now question to all of you is, what is wrong with this approach? This approach looks just perfectly fine, but what is wrong with it? Yes. Time consuming. Okay. It would not take forever, but yeah, it'll be slow. That I agree. Yes. Any other problems do you see with this approach? So can it process, say, 10 gigabyte of data? Yes, thank you, Isa. Yes, if the size of the book becomes bigger, then there could be problems, right? Because this dictionary that you see here, word count, is actually staying in the memory, right? It is staying in the memory. So the problem is it cannot process the data that is not fitting into the memory. Okay, and that is something, the biggest challenge in computing. And all the naive programmers, they end up with, when they start coding, they realize that they have overused the RAM. And trust me, 90% of the programmers will actually go with this approach. Okay, they somehow are so used to the hash table that they can't all the logic they write is around hash table, and there's nothing wrong with it as long as you know that the data you're putting in hash table will fit in the RAM. The approach is great. All right, so you cannot process data beyond what can fit in the memory. All right. The second approach which Isha had suggested was to break the books into one word per line, right? And then insert one word per row in the database. Correct? Correct. And some other person has also suggested a similar approach. And then use select word comma count star from table group by word, right? Is this approach clear to you? This is something which I would do if my boss asked for the same, right? Or I'll use the next approach. The next approach involves Unix. Okay, how many of you are comfortable with Unix? All right, so can you do it using Unix command? All right, so approach 2 is, okay, let me explain again, sorry. So what will you do is you'll create a temp table as suggested by Isha, that you'll create a temp table with having only one column. You'll have only one column, right? And in that one column will be one word, okay? And then all we'll do is we will do select word comma count star from the table group by word. So basically we group the data by the word and then did the count star for each word. Is it clear now? This is approach 2. Approach 1 was programmatic. All right. So this is a practical approach, and most of us would actually do this faced with this kind of challenge. Now, this one does not suffer from memory problems. Why? Because database can handle the memory issues easily. And yes, we will have to still read the whole text that we cannot avoid anyway, right? But it is being read from the same machine, single machine, so it might take a long time. All right. The third approach could be a Unix approach. All right. So I'll just take you quickly through Unix program before I explain to you the approach. Is that okay with everyone? I want to explain to you what is Unix pipelining. Is anybody following the Linux tutorial? It's a nice tutorial. You must try it out. Okay. So where is, yeah, this one. You must try the Linux tutorial. Oh, great. Oh, great. All right. So you must try out Linux, and Isha has already completed it. Good. Wonderful. Wonderful. All right. Okay. So I would love to explain to you uh, how does a Unix pipeline work. That's the third approach I'm going to take, but for that, I would love to explain to you. All right. So, and why I'm explaining this is because this is going to be useful in in solving many problems. Okay. In solving many problems, this is going to be very useful. All right. You will see that in Kafka processing. You will see that again in the Hadoop streaming. You will see that while processing data with Spark, we are going to use Unix pipeline from time to time. All right. It's needed. It's something not, something which is a very powerful thing. My request to all of you is that most of the big data systems and most of the systems around the world rely upon Unix pipelines. Okay. and Unix command pipelines to be specific, and most of them actually run on Unix. So it'll be great. It's a great skill to have, to know Unix or Linux. Both are same. They share the same kind of architecture, same kind of commands. So learning Linux is absolutely a great skill. All right, learning Linux, whether you are developer or you are an architect, you are anybody, is going to be a big addition. All right. In my past, I have mentored so many people, and most of them have, done pretty well in their careers after they have got hang of Unix and SQL. Unix, SQL, and one programming language is something I always recommend everyone. All right. So I'm going to take a quick, look at the Unix pipeline. So what is a Unix program? A program can take input from you. That's a program. Program may also print some output. For example, here, when we say ls, it prints the results, right? Like here, where was my console? Did I close my console? Let me open the console. All right. I'm sure that everybody has logged in, and so here the console is basically a Linux console. So when I type a command like ls, it prints me the list of files. So this is the output of command, right? ls did not take any input from me. Okay, let me just pull it out in another table and another tab and keep it here. All right, so a program may also print some output. Now, a program one can send the output to another program by putting pipe in midway. ls can send the output to another command. All right. So if you have command one, pipe command two, it's essentially the output of command one, instead of coming to the screen, goes to the command two as input. All right. That's the Unix command. So here, let me explain this approach to you in parts. Okay. Let me explain this approach to you. Let me break it down into parts, and then you will have a better clarity. Okay, so all right, this is something that we were discussing yesterday. All right, so you can see the command. Does it look very cryptic to you? Okay, so how many commands does it have? A single pipeline? All right. So what does this command do? Cat my file. Yes. Anybody? It shows the content of the file, right? So let me just say cat 27. What was that? 27 May sample. Okay, but it doesn't have a repeating word, so it won't be fun. ls minus l star.txt. Okay, so I have big and okay. Let me just create a new file, right? Say out of 100 lines from big.txt, and I'm saving it to small.txt. You can see that most of the things can be easily accomplished by Unix commands, right? So here I've just taken 100 lines from the original one. It has some random words here. Okay. And or maybe should I take beginning lines maybe. All right. So here is our file. Now what am I doing? Here I'm saying cat small.txt. What does it do? It shows the content on the screen, and it was little bigger. So I put a pipe and send the result to more. And what is more doing? More is showing the data page wise. Okay. So the data from cat is going to another command more, and more is displaying this result, right? So here it shows that it contains the books from Gutenberg, Sherlock Holmes books. So we've just taken 100 lines from it. Okay. All right. So that's cat small.txt. Okay. Then there is another command called sed. What does sed do? Sed substitute a particular expression with another expression. Here we are saying substitute space or tab. Slash t means tab, space, and square bracket means either of these two characters. Plus means any number of things that are by captured by the character before. So any number of spaces or tabs will be captured by SCD, right? In the input. From the input, it will replace spaces and tabs with slash n. What is slash n? It's a new line character. So it'll basically substitute space and tabs with new line, meaning it will leave only one word per line. Okay, let's take a look. Is everybody with me so far? You can see? You can see this? Maybe I can make this window a little like this. Yeah, this is better. So you can see that it has broken down all the words in such that there is only from here there is only one word, the project Gutenberg ebook and so on, right? Then I'm passing it to a command called sort. What does sort do? Whatever data comes as input to sort from the pipeline, it sorts that data. Okay, let me show you how does it work. If I type a sort command, so instead of reading from any pipe right now, it's waiting for me to type the result. This is a sentence, okay, of a book, right? And to end my input, I'll just press Control D. So you can see that it has ordered the data here. A book is of sentence this, right? Correct? So whatever input that comes to sort, it orders the data that line by line. Okay, it has ordered this data line by line. Clear with sort, right? Similarly, if you want to test SED individually, we can try here. Okay, we'll say this is a line. You can see it has quickly replaced spaces with that. All right. So SED is working fine, sort is working fine in isolation, and they are also working fine this way. Now let's give the output of SED to sort. Okay. So you can see that the data is ordered. You can see the data is ordered. All right. And then we use a command called unique. Unique is a command that expects the input to be sorted. That's why we are using sort command. Okay, you can see that it has computed the frequencies of words. All right, what is minus S1G? It restricts sort to not use more than 1 GB of RAM. Minus C of unique command displays the counts. If we just give unique without minus C, it won't displays the count. It won't display any count before it. All right. So now you can see. All right. Now, if I want to sort the data based on the frequency, I can further pass it to sort command, right? And if I want to see it page wise, so I can see it page wise, right? You can, what you see here is the is most popular, then of, and then new line character, and then and, and so on, right? So that means this command has worked pretty well. Okay, this command has worked pretty well. Is everyone okay with me in this? All right, so this is Unix pipelining. The third solution is Unix pipeline, right? Third solution is Unix pipeline. Now, we talked about approach 2 and 3, SQL and Unix. Both of them do not suffer from memory related problem. What kind of problem do you see with approach 2 and approach 3? Approach 1, the programmatic approach, was suffering from memory overflows. Therefore, we used approach 2 and approach 3. They do not suffer from memory issues. Now, what kind of problems do you see with approach 2 and approach 3? Yes, right. Thank you, TJ. Since it's a single CPU, more data will make it slower. That's right. Or, as we discussed earlier, rather than machine, it will be basically the discrete speed. Correct? So the problem is CPU, disk speed, disk space, and so on. Right? Now, earlier before Hadoop, how we used to solve this problem? We used to use multiple computers. All right? This way. We used to call this approach as external sort. Right? So we'll discuss this approach as well so that we all agree with and at least start thinking in terms of distributed computing. All right? So we'll continue from here in the next week, and probably next week is going to go mostly in MapReduce. All right. So all right. So see you next week, and I look forward to your questions. Feel free to reach out to me if you have any questions. All right. Thank you, everyone. Sure, sure. Shilpa is saying also videos as in. So videos are located here. Are you able to see them? The videos are located in the instructor-led course. If you click on my course, okay. If you click on my course and the last one here, if you go again into it. So here you will see there are these courses. Here you can see this is the first video. This is the second, third video. All right, great. So I'll be adding to this one only. All right. So thank you, everyone. I look forward to see you next week. Bye-bye.